My name is Michel, and this is Mattia, and together we co-authored MobX-State-Tree, and we first met last evening, very late. And the cool thing is, what we discovered is we have the same taste of cloves. How good is that? And so actually, we did some research into Verona, and it turns out that you guys love opera. Now, I love opera as well. It's really, really great, truly awesome. I used it for years. Opera is great. But we're here to talk a bit about state management. And state management, like opera, can be scary or intimidating at first. So let's take a very quick recap on how you can approach state management, because you heard already a lot of it today. So there are different approaches you can take. So first of all, you can stick to set state, and that's pretty great, especially if your state is only relevant for your component tree. So that might be just enough, as we heard this morning. But secondly, you can of course use Redux, which is also really great, especially if you get paid by the hour. And third one is MobX. And MobX is also great, especially if you believe in things like magic and casting spells to get things done. But finally, if you really want to be my true hero, you should be doing this. You should be using jQuery data with component graphs to store your state. But so anyway, let's focus a bit on the two approaches that take state out of your component tree.
Yeah, when we speak about those two opposite patterns, we speak about MobX and Redux. But why are they opposite? They are opposite because when we speak about Redux, we are speaking about immutable objects. So that means that we cannot change properties in our object. And while using MobX, instead, we can change whenever you want on whatever object you want. And you may see that there's a winner between those two approaches. But as developers, we may not find the real final solution. We must think about the benefits of each one and choose which one whenever fits your needs to get the best for your application. But let's have a look at both of them. For example, here's a to-do reducer in Redux, and as you may see, the code is not much clean about your application state shape, because if you have a quick look at your code, you see that you cannot tell which are the properties, which are the actions of your code, and that's predictable because with immutable objects, you are focused on creation of new objects. So your code will be always about transformation rather than data shape. And what we did, we have actions which are not collocated with reducers. And when you work with a huge code base, that could be an issue, because if someone new enters the project, doesn't really know immediately where the action implementation is really, and so it became really, really hard to find that. On the other hand, the MobX community almost always uses EX6 classes. And that's really nice, because just having a look at your code, you can see easily which is the shape of your state. And you also get collocated action, which is really, really nice, because you can collocate your action. So in your file, you will have whatever you need for your entity. So with MobX, we have explicit data shape, while with Redux, it's kind of lost in all of our code, so it is implicit. But let's have an example about data redirection. With Redux, it's really easy to redirect our data, because our data won't contain any application business logic. And that's really awesome, because we can just pick our object came from the server and stick it into our reducer, and it became part of our state tree. So that is really, really, really awesome. But with MobX, unfortunately, it's not so easy, because we are using classes, and classes have an internal state. So we need methods for both serialized and deserialized state onto and from our class. And that means really a lot of line of code just to do that. With MobX, we just said that we usually use classes. We can have whatever data shape we want, and unfortunately, data serialization, deserialization become really hard. While with Redux, we use plain object, so we can use only tree structures, and serialization is usually in objects, in actions. As Michel said, it can become a really Christmas tree. But all those Redux snapshot benefits are really awesome because thanks to immutable objects, we can provide things like time travel, we can make our testing easy through snapshot testing, and thanks to those properties, we can even make better dev tools. Redux dev tools are awesome. There's nothing compared to them. And if we really want all those benefits in a mutable world, what do we need? To get them for free, we basically need to know which is our data shape. Because if we know our application entities and we know their shapes, we can just provide function that basically for free does a serialization and serialization through and from our observable object. So it would be awesome to have the best of both worlds, the best of Redux and the best of MobX. Well, you can, and you can with MobX-State-Tree.
So MobX-State-Tree is kinda, hopefully, the love child between Redux and MobX. And so let's take a little dive into it by just building a small application with MobX-State-Tree. And for that, we take the all too familiar and also all too boring to do MVC application. And so this application is, at this point in time, completely static. So there are components, and they render the data they receive, but they don't do anything with them. They don't really have actions, and they don't listen to the data. And the data or the state itself is just a JSON blob. So basically, we're here at a point where we just have a mock-up of our application. And so even if we click a to-do item, you'll see that nothing changes for the simple reason that there's no event handlers and no state. There's just data. And so what we do when we start working with MobX-State-Tree is that we're going to declare the shape of our data. So it's really declarative, telling what our data looks like. And because we declare the shape of our data, we can start reasoning about it. And so here you see, for example, we define the to-do type, which defines the three primitive attributes it has, like text and completed and ID. And for some, we provide default values and we infer the type, and for the ID, we just declare it's a number. And then the store is basically a composition of some literal strings, which form together an enumeration, and an array of those to-do items. So now we have a declarative description describing our shape. And it's really great because we can do a lot of interesting things with types. We can do runtime type checking, but we can also do design time type checking. And in the future, we could also generate GraphQL schemas from that, or the other way around. We can convert from or to JSON schemas, etc. And so the type system is quite rich. It's based basically on the tcomp library. It took a lot of inspiration from there. And you have a few collection types, a lot of primitive types, but also a lot of higher order types, so that you can compose new types, and it's actually pretty powerful. But there's more of types. So types are not just nice for describing what data looks like and for verifying that. It's also really suitable to attaching behavior to a type. So for example, once we have the types, we can start by instantiating a store by feeding data into it. So we take the JSON we have, we pass it into our store, and we pass our store into the component tree. And then we literally still have the same application, but now it has a MobX-State-Tree. And this didn't achieve anything yet for us, but now we can start attaching behavior to our types. So on our types, we can start adding actions. And actions describe how a certain instance of a certain type can be modified. And actions, they're basically produced by running a function with the instance on which they operate. And so that avoids all kinds of binding problems. And the best thing is that the actions themselves are still really straightforward. And the basic reason for that is that we can just modify an instance. So we're not required to produce a new state tree or something, we just modify our current instance. And because we solved the binding problem, we can also now just attach our handlers directly to our components without needing to worry about things like this not being correct and such. So here we just add a complete action to the checked on change state. And finally, we can now click our to-do items, except that you won't be seeing anything. And the reason for that is that we are actually now modifying our data, but since the data lives outside of the component tree, React doesn't know about it. But luckily, that is super simple to solve for the sole reason that MobX-State-Tree is based on MobX. So we can introduce the well-known observer decorator onto our components, and it enables React components to just track any data that is relevant for the rendering. So we just slam observer on all our components. We don't worry on how the state should map to props and those kind of things. It's just tracked for us, and the components are now made completely reactive. And this should all be enough now to have a working to-do list. So we can now check and uncheck, and by just adding observer, exactly each component knows where to listen to. Now, there's another fancy thing I want to show you, is that although we declared our own types, TypeScript is still able to reason about it. So if we say Visual Studio Code to use the TypeScript compiler in this file, which is nowadays really easy, you can see that we defined our own custom type and our own custom MobX-State-Tree library, but still TypeScript is able to provide auto-completion on the types we just defined, and even do some error checking. So if we assign some wrong type to it, the TypeScript compiler will flag this off as you are incorrectly using this to-do shape you defined. So that's a really powerful feature of TypeScript, actually. So let's add some more complex actions. And especially in this example, the action that adds a new to-do item is very interesting. So what we do here is we simply put a new to-do item on top of our to-do list. But the interesting thing is we don't instantiate actually a to-do item. We just provide a snapshot, a description of the state of that to-do item, and push it into the list. But because MobX-State-Tree can reason about the shape of our data tree, and knows that because we pushed into a to-do list, it has to be a to-do item. So even though we just pushed some plain data onto that list, we will see that we actually can now use the behavior we have from our data definition, from our declarative data definition, so we can invoke methods on this to-do item. And that's because we can infer all this information. And we can even attach more behavior to types than just actions. So for example, we can also introduce views. We can introduce derived properties. And they are driven, again, by MobX computed values. So we can just introduce some complex computations. And we know for sure that MobX will invalidate those computations at the most smart moments. And by using them in our components, that will automatically subscribe those components to any future changes in those derived values. And now, as you can see, one of the nice advantages of having this all in our state tree is that even complexer components just stay function components, because they just track the data they receive, and they really don't have to have their own state anymore or lots of complex handlers. So the next interesting thing is that so far we've been talking about mutable instance trees. However, MobX-State-Tree, as said, it knows the shape of our data, and so we can get our serialization for free. And that is something we're going to leverage. So in MobX-State-Tree, there's this concept of a snapshot, and a snapshot captures the entire tree, the entire state of your tree in a single plain JavaScript object. And that object is structurally shared, and it is immutable. And what happens is, if you change your tree, in the background, a new snapshot gets generated for you, and reusing as much as possible from the previous snapshot. So it basically takes away all the boilerplate from you of producing a new state. It just does that for you in the background. And now we can do something cool, like we can start listening to all those snapshots and use that to leverage that to use local storage. So what we want is that if we reload the application, it tries to grab the state from the local storage and inject that state in our tree. And then we can listen using the on-snapshot listener to every time a new snapshot is available, and just write the snapshot immediately into our local storage, which is straightforward because it's just plain JSON. And so, as you saw, when we reload the application, the state is now preserved. And of course, when we have snapshots, that means that we can build the most cool yet unused feature of state management ever, which is called time traveling. And so this is what we can do now with that on-snapshot listener. We can basically create an array of all states that ever exist in our application and attach the on-snapshot listener to our store. Whenever we receive a new snapshot, push it onto the states we have. And then undoing or traveling back in time is just a matter of grabbing an older snapshot and applying that back to the store, back to the tree. And this is where it really gets interesting, because what apply snapshot does, it doesn't just reconstruct the entire tree. Now it's really smart. So it will take your current state and will determine what are the minimum amount of changes needed to bring your current state in sync with the snapshot you provided. So what it is effectively doing is reconciliation. To-do items which aren't changed in the snapshot will stay as is, and things that have changed will be updated. So it's basically the same as what React is doing for your DOM, MobX-State-Tree is doing for your state tree. It reconciles and updates your state as smartly as possible. And so let's add the time traveling to our little application. So there's a reference implementation of doing time traveling, following the pattern you just saw. And the interesting thing is that the time traveling implementation is implemented in MobX-State-Tree itself. So we have a model of time traveling, and we just put that into our store definition we already have. So we add the model of time traveling to the shape of the store, and we just give it one default property, and that is to which part of the store it should listen to. And so if we now go to the application, we can see we can undo our changes we made. But what's even cooler, because the time traveler is in our store itself, we can now reload the application, and the state of the time traveler is stored in the store, so we preserved our undo history. So even our undo history of the store is part of the store. It's kind of confusing maybe, but it's really cool that we just can serialize our history as well. And I can very quickly show you how that roughly looks in implementation. So this is the definition of our time traveler. The model is that we have a history, which is an array of immutable objects, and the types that frozen represents anything that is immutable, because if it's immutable, it doesn't care how it looks. And we have an undo index, which is basically the point in time where we are now in the time traveling. And we have a target path, which is the string specifying to which part of the state we want to listen to. And then we have some local state, which only exists as long as the time traveler itself lives. So this is very comparable to what you have in React components, where you have also local state, which is internal to the component itself and only valid for the life cycle of the component. And so then we can register a hook that after this time travel has been created, we find the store it should be listening to. And because MobX-State-Tree is a completely fractal structure, every node in the tree is a tree itself. So we can just start listening at the snapshots of a certain part of the subtree. Well, this is what we do here. So we listen to that part of the tree, and every time we get a new snapshot for that part of the tree, we store it. And we also save a reference to the disposer function to be able to stop it later on. And so then, undo is still the same implementation as you saw before, just apply back the snapshot to that part of the tree. And then if this time traveler is ever disposed because you throw away your store or something, there's also a lifecycle hook for that whenever the time traveler dies, we dispose our subscription. And so types have actually defined also the lifecycle a bit like components do. So this is really great if you want to store resources like data subscriptions in GraphQL or something. I want to have them disposed automatically once the data disappears from the tree. So it becomes really declarative. It's the thing React did for UI, we now do for state. So now it might look like we have an actually nice undo redo implementation, but actually we don't have a nice implementation. And it's very easy to demonstrate that. So suppose that our to-do MVC application is receiving updates from the server or from other users. Now we're going to simulate that in a bit stupid way. We're just creating an interval function which every 5 seconds adds a new to-do item to our to-do application. So every 5 seconds it is as if the server sends an update to add a to-do item. Now if we are going to work in our application and we add some new to-do items, and in the meantime we see also the updates from the server coming in, and now we start going to undo, then something weird happens. We start to undo the changes of the server as well, which might be okay for debugging, but it isn't for a real user application. If a user is undoing changes, he should be undoing his own changes, not the changes of some other user. So time traveling isn't fit for undo redo in a multi-actor system. To do undo redo really on the level where a user can use it as a feature, we should be doing something else. And there are, roughly speaking, 2 approaches to undo redo. And the first one is the patch-based approach. So whenever the user undertakes an action which starts modifying the state, we are going to record not which new state he produced, but we're going to record how he changed the tree. So that is basically recording patches or recording deltas, describing how his actions changed the tree, rather than in what tree it resulted. And that is conceptually very similar to what we're doing when we're doing a git revert. So if you're doing a git revert, you're not going to rewind your git history to, let's say, 2 weeks ago, because then you would lose all other changes as well. Now you just take a look at a patch you were doing before and what you want to undo, and the inverse of that patch, that is what you are going to apply to your history. So you add more changes to undo previous ones. And that is the power of patches. A second approach you could take, which is a bit less flexible, is that you go back in time to the place where you want to undo something, and then you skip that action where you modify something, and then you replay all the other actions you received. And that is very similar to what you can do when you do a git rebase, where you do it interactively and just can skip some commits as a way of undoing incorrect changes. And both can be implemented in a MobX-State-Tree if you want, but for now we just do the first one, the patch-based approach. And for that there's also a reference implementation in the library, and it's called Undo Manager. And of course, Undo Manager, again, is implemented as a MobX-State-Tree model itself. So we can just make it part of our store. And we're going to make a small change to our simulation of the server, because we now actually want to mark, to indicate that whatever the server does shouldn't be considered a user action. So we tell the undo manager that the update the server does shouldn't be recorded in the undo management. Which doesn't make sense if you're choosing snapshots, because even if you wouldn't record it, it would still be part of the next time the user changes something. But if we're recording patches, we can safely do it. So now we can start making changes. And we can also wait for server changes to come in. And if we now undo the changes, we see that we are only undoing our own changes. The server changes are not part of the history of the undo manager. And the only reason why we can do that is because we've recorded patches. And patches are very powerful, but the problem is you cannot get patches from immutable data, or at least you cannot get them cheaply. Because to produce a patch, to describe on this object that attribute has changed, you need to be able to listen to fine-grained changes in your state tree. And so that is something MobX can provide for us. And so if we take a quick look at the implementation of that undo manager, the essence of it is that we add middleware to the store, and then whenever an action starts, we instantiate a patch recorder for the store, so we start recording patches. And of course, actions cannot be just synchronous, they can be asynchronous, they can take multiple steps to produce the end. But asynchronous actions are a first-class concept in MobX-State-Tree, so we can define hooks for whatever happens if an action suspends. So it means that you just start and wait for a promise to resolve. And later on that promise resolves and action continues, and then the resume hook of the middleware gets triggered, so then we resume recording patches. So that way we know of all the patches generated from an action, even if that action takes multiple ticks of our JavaScript engine. And so in the end, what we simply do is, if we undo, we just take all the inverse of all the patches we recorded and we apply it to the tree, and then we're back where we wanted to be. So far we have talked about a few interesting concepts on the basics of a MobX-State-Tree with actions and the properties describing the shape. And also we have talked about reasoning in more generic patterns like reasoning in terms of snapshots to do time traveling and patches and middleware. But actually there's something interesting going on here. Basically, because MobX-State-Tree always produces an immutable representation of your tree, we can actually make MobX-State-Tree act as if it is a Redux store. So we can translate some terms. So the state of a Redux store is the same as the snapshot of a MobX-State-Tree. And a subscribe listener, where you receive new states, is basically the same as the onSnapshot listener for MobX-State-Tree. And actually we can do a dispatch as well, because we have apply action, which you can very nicely combine with middleware, and where you get a serialization of the action just before it's applied. You can record those invocations as well and apply them later on. And instead of React Redux connect function, we can use observer. And with that, you can imagine you can create a very simple wrapper function, which is available actually as a Redux store, which gives a MobX-State-Tree the same API as a Redux store. So now we have that, we can do something very funny. We can connect a MobX-State-Tree tree to the Redux DevTools, because it implements the API. So we can very quickly demonstrate that. So we're using the official remote dev library, which is typically used in Redux applications to connect to the Redux DevTools. And we pass it our MobX-State-Tree store. And we import the tiny wrapper utility that converts that. And now on this do application, we can simply open the Redux DevTools. And if we start changing something, we see the Redux DevTools recording the actions we are invoking. And actually we can even use the Redux time traveler to travel back in time. So that basically proves that it becomes a superset. So that was in essence what we want to share with you today. So MobX-State-Tree allows you to very declaratively describe your problem domain, and after that leverage the best features of both immutable and immutable approaches of state management. So get rid of the boilerplate, get the full reactivity, but also be able to write the generic tools which comes with having snapshots and such. So with that, I want to conclude. So install the library, start it, and thanks for listening.